Chapter 8, Lesson 5 of Geometry. Now that we understand what angles of elevation and angles of depression are, let's look at how we can apply those and use those for indirect measurement. Now, surveyors will use two instruments, the transit and the theodolite, to measure angles of elevation and depression. And what they'll do is on both instruments, they'll set the horizon line or the horizontal line perpendicular to the direction of gravity. Gravity pulling straight down. If we go perpendicular to that, we're going to have a horizontal line. And then we can either look up and have our angle of elevation, or they can look down and have their angle of depression because they have their horizontal line fixed. And then, like it's sketched out here over here on the left, then if you know the distance from the figure that you're measuring, you know the angle of elevation or the angle of depression, then you have this vertical height which you're trying to determine. You have a nice triangle, you have your trigonometry set up, you have an angle of elevation that you can use to measure the heights of different things. So you can see this quite a bit out there in surveying, whether we're building something or those types of things, and you've seen those around. So let's talk about then how we're going to use these angles of elevation and angles of depression to solve problems that we're going to do. Now, as we've stated, angles of elevation and angles of depression are applications of trigonometry, and therefore what we learned in the previous two lessons when we were dealing with small triangles that were drawn for us, we can apply that now to real-world situations simply by superimposing triangles on the real-life situation. So if you're given a diagram, then that's kind of easy, but if you have to draw one for yourself, you're going to need to read the problem and draw a diagram that illustrates the situation. Now remember, we have to have a right triangle, so when you're reading the description of the problem, you want to think about, well, how can I make a right triangle fit this situation? And then how does each description fit the different sides of the triangle? Some things to remember. Line of sight is going to be the hypotenuse. It's going to be what you're looking up for. If you want to measure the height of something, that's the vertical line of the triangle. If you're measuring the distance from something that you're standing, then that would be the horizontal line of the triangle. So some of those things you just need to remember as you're reading about how they fit into the right triangle that we're trying to superimpose on the problem. Once we have the triangle drawn and the sides labeled, then we can determine which ratio we want to use. So labeling the problem, drawing the diagram, that's the key part of all of this lesson. The trigonometry, hopefully we have in hand because we've done those in the previous two lessons. Once we've, again, drawn the diagram, applied the or chosen the appropriate ratio, we simply then substitute in the values and solve like we did in the previous lessons. So I'm going to do a couple of examples. I won't work out all the arithmetic for you, but I'll do a couple examples where we will read through the problem, show you how we can try to set up a right triangle for that, and then we'll leave the calculations for you to do on your homework. So here's a situation where Miguel looks out from the crown of the Statue of Liberty, which is approximately 250 feet above the ground. So as I read that, okay, I want to think about, okay, right triangle, where is he? How does this apply? So he's in the Statue of Liberty, so he would be up here. And then here's the ground, and it tells me that the height is 250, so I know that the vertical height is 250. A couple of things here. When it says above the ground, that's kind of an idea or something you want to recognize as being vertical side of the triangle. And again, the whole idea behind the application is being able to draw these or sketch these figures out for ourselves. So he's in the height, or he's in the Statue of Liberty. He sees a ship coming into New York Harbor and measures the angle of depression as 18. So he looks down, so his line of sight, as he looks down, he sees this ship that's out here, okay? So he sees that. So as he looks down, there's my line of sight. Here's this. And now remember, here's where we don't want to make the mistake, because we'll draw this triangle, and as I said, what most students will do is they'll want to put the 18 right in here because they know that they want the angle inside the triangle. They know they're going to use this, and so they just put it here rather than thinking and remembering about the angle of depression. It has to have a horizontal side to it. And if I put 18 here, this is not horizontal, and neither is the line of sight. So remember we talked about there's this imaginary horizontal line, and then to look down he has to look below this line. So this is the 18-degree angle of depression. Now, as we stated, we're going to want, well, let me read the rest. Find the distance from the base to the statue, of the statue to the ship to the nearest foot. So this is what we want to know. So we want to use this triangle, we want to use trigonometry, and so we need an angle inside. And so again, the tendency is to want to put that here because we know we need an angle inside, but that's not the angle of depression. This is the angle of depression. But we can use what we know, that the angle of depression and this angle of elevation inside are congruent because they're alternate interior. So I can put the 18-degree angle in here, and now I have an angle inside the triangle that allows me to use trigonometry. So once I have this sketched out, I can then say, okay, here's the angle, this is opposite, this is adjacent, so which ratio should I use? Well, tangent ratio uses opposite and adjacent, so I would use that, and so then I would write my ratio. The tangent of my angle, which is 18 degrees, is equal to the opposite side of 250 over the adjacent side of x. Now, some of you might be wondering, well, how is it going to be any different than if I put the 18 in here? Well, if I put the 18 in here, I still have tangent of 18, but this ratio would be the reversed. The opposite side would be x, and the adjacent side would be 250, and you can see that that is not going to give me the same answer as 250 over x. So it's important that we get those in the right place. And then you would go ahead and then round that off to the nearest foot once you calculated it. In this example, we have the world's tallest unsupported flagpole is 280 feet tall. And again, whenever we're talking about how tall something is, that's the vertical side. So this is 282 feet. Now, the shortest shadow cast by the pole during the year is 137 feet. Now, if you think about the sun shining down, the shadow is cast on the ground, so this would be the shadow of the pole, and that shortest shadow is 137 feet. It says to the nearest degree, then, what is the angle of elevation of the sun when the shadow is the shortest? So, again, my angle of elevation, this is the question, what's the angle of elevation? So I have my flagpole, I have the shadow, the angle of elevation has the horizontal and then the shadow or the line of the sun, and so this would be my figure. So now once again I have the triangle drawn. I need to decide which trigonometric ratio is what is going to apply. So I have my angle, I have the opposite and adjacent, so again I'm going to use tangent. The tangent of this angle, which I don't know, is the opposite side, 282, over the adjacent side of 137, so then I would solve this using the inverse tangent and then calculate it. Okay? One reminder here, not that it came up in this situation, but just remember when you're writing this ratio that these units will have to be the same. This is in feet, the height of the pole, and the shadow is also in feet, so I'm okay. But if there was, one in inches and one in feet, or one had feet and inches and something or other, you would need to convert those to the same unit in order to get the correct calculation. One more example really quickly to help you out with, so as you see this you can tackle these in your homework. A meteorologist measures the angle of elevation of a weather balloon as 41 degrees. So we have an angle of elevation that's given to us. So we need a horizontal side and we need the line of sight or angle of elevation looking up, and this is 41 degrees. The radio signal from the balloon indicates that it is 1,503 meters from his location. So which side of this is 1,503 meters? That is the question. Now it's 1,503 meters from his location. To the nearest meter, how high above the ground is the balloon? So I know this is x, so the question is this the 1,503 meters or is this the 1,503 meters? And this becomes the most difficult part of the problem. Well, if you think about it this way, a radio signal from the balloon indicates that it's 1,503 meters. So the meteorologist is standing here and he is getting a radio signal from the balloon. So which path would the radio signal follow? If this is the balloon up here, I don't know if that's much of a weather balloon, but where would the radio signal come from? Would it come along this line? Or would it come along this line? Well, it would come along this line because he would have to receive it directly from the balloon. The radio signal wouldn't come from here to him because this is not where the balloon is. So this is going to be your 1,503 meters. So once I have this drawn, then I can now again decide which ratio to use. So I have an angle. This is the side that's opposite of it. This is my hypotenuse. So opposite and hypotenuse, that's the sine ratio. So I'll use sine. So the sine of my ratio, which is 41, or sine of my angle, excuse me, 41, is the opposite side, which in this case is x, over the hypotenuse of 1,503. And then I would solve my equation. Okay, so angles of elevation, angles of depression. Remember what you know about angles of depression. Those are not inside that triangle, so you're going to need to remember how to get that angle that's inside the triangle. When you're reading a problem, again, right triangles are the key. Superimpose the right triangle, label the sides with the appropriate measurement, and then use trigonometry to solve.